Okay. All right. So we're going to conclude today with the section on PVT lab experiments, Chapter 6, and there's probably enough time to get started with the next topic, which is our last topic in PVT related to the book. The last topic being Blackwell PVT properties, which is Chapter 7. And as part of today's lecture, which will talk about the constant volume depletion test, there's a paper by the same name evaluating constant volume depletion data, and this is on the website. Let's see, website. It's Learning. Well, not It's Learning, but it's on my website. Tab teaching. Under handouts, that's not it. There it is. CVD, widths and torque. So this paper covers a lot of what's the topic today in more detail than you probably need. But at the same time, that paper also is kind of the paper where we introduced the method for creating general Blackwell PVT tables, which it's still used in pretty much all the software and in the industry today. So in this paper, which I recommend that you do read, it talks about the topic today, the constant volume depletion test. It talks about the Blackwell PVT tables and methods, which is kind of a short version of Chapter 7. Probably all you need to know is in this paper here. And the paper also gives the origin of this K-value equation that you used in the one exercise, where you have convergence pressure and the Hoffman-Crump-Hocott method. That set of equations was also presented for the first time in this paper. So this paper has a good chunk of the things that are relevant to the class. So I think it's worth a read. Probably more important to have read and understood this paper than a lot of the details in Chapter 6 and 7. So that's out there. Steenbutter-Torp, he was one of the students when I came in 1978. He was, I think, maybe fourth year out of. Back then, it was a 4.5 year program. It didn't have the title Master of Science. It had the title of Civil Ingenieur, and the Steenbutter, he is, I think, still a lead engineer at Statoil at the research center. For many years, he was working in reservoir, and I think he's now been the head of this drilling group in the research center here at Grotvoll. He was many years, I think, kind of in lead roles for different fields in the Statoil portfolio. The first 10 years, I think he worked for Esso in Stavanger before he went to Statoil. So he's a great guy. He's local Trønder, and from Trondheim, and so anyway, he is the co-author of that paper. So that's a paper worth looking at. Any questions before we start on this last PVT experiment about things we've talked about from the other experiments? Okay, we talked about the constant composition expansion test, which gave us our saturation pressure, and it gave us properties of the single phase, namely the density as a function of pressure above the saturation pressure. We talked about the multi-stage separator test, which tells us how much sellable gas and sellable oil we get from a particular reservoir fluid. which is important. And optimizing the conditions of the surface separation, I hopefully convinced you that could be important to revenues. And then we discussed the differential liberation test, which is specifically for getting properties of oil systems, mainly the oil phase, but it also gives you properties of the gas, equilibrium gas that develops or evolves from the oil as pressure drops below the bubble point. And then we talked about how to combine the differential liberation test data with the separator test data to create a version of black oil PVT properties, which is not used much anymore, but we went through that. So that's kind of where we've gotten so far. So now we're going to talk about this last PVT experiment. I think this is a little bit smaller than... Okay. So we're going to talk about the constant volume depletion test. And this test is mainly conducted on gas condensates, reservoir fluids. So that's reservoir fluids with a dew point. And it can, in a few cases, be used for what we'll call very volatile, or sometimes we refer to it as near critical oils. Okay? So can be used for gases, gas condensates, and or oils, but the oils that it's used for would typically be very, very volatile, high gas oil ratio oils. And of course, Curtis says, hi, I have to give you a number because I'm not a politician. I can't just say things are high and things are low and expect you to believe me. So I would say that probably if you have a reservoir oil that has a gas oil ratio greater than about 2,500 standard cubic feet per stock tank barrel, which for you metric people would be about 500 standard cubic meters per standard cubic meter. Okay, and there's a few fields like that in for example, the North Sea. Smerbrook South is one of them. Yeah. So these are the types of fluids that we use this test on, and what's really the key data here being measured is really it's the gas composition, how it changes as you go below the saturation pressure. So the key data being measured here is how the gas composition changes as we drop below, actually not equal to, because we know the composition at the dew point, as the pressure drops below the saturation pressure. Okay? That's the main data. In addition to that, well, before we leave that, what's particularly important is how the liquid forming, the components that make us most money, that's like C4, C5, C6, and heavier, because we can sell it as a liquid. And as a liquid, it has a value 3 to 10 times more than sold as a gas per molecule. Okay? Depends on the gas and oil prices. But so we're particularly talking about this C in plus. I would say probably C5 plus is what you want to look at. Those are the components that make up this thing that we call oil that we sell. So the reason that's important is because the value of a gas condensate reservoir will primarily, the economic value of a gas condensate reservoir will almost always be primarily from the condensate that's sold or the oil that's sold at the surface and not the gas. Okay? So you're going to make more money off of the oil being sold than you all are going to be selling the gas. And so if the amount of oil that you get out of a certain reservoir volume of gas produced, if that amount of oil starts dropping, which it will as you go below the dew point, that will have a big impact on the economy of the field. So knowing exactly, so basically these are the surface oil, what we usually call surface condensate, forming components. So, and these are typically the components that dominate the revenue for gas condensate reservoirs. In the E-note, let's see if I can find that. In this so-called E-note for gas condensates, let's see, that's, I'll have to unzip these. Gas condensate. I'm not sure which one of these reservoirs. There we go. There's an Excel sheet in the GC reservoirs. It's just kind of a general description of gas condensate reservoirs. There's an Excel sheet called condensate value, which is a little calculator to help estimate the value coming from the condensate versus the gas. So you can open that up if you want to take a look at it, but we can pull some numbers in here and change the prices of gas and oil, which are very different now than they used to be. So this basically gives the value of surface condensate and gas production from a gas condensate reservoir. You put in a gas price, an oil price. You can see the last time I used this, it was low compared to 2 years, and it's high compared to today, so we have to put in something like $33 maybe, 32, something like that. Now the gas price in Norway is very different than the gas price in the United States. In the United States, the gas price is probably $2 per 1,000 cubic feet. Whereas I'm not sure what it is. It depends which gas is being sold in Europe. It might be relatively high for Norwegian sales. I'm not quite sure, to be honest. Anybody know what the gas price of petrol gas is today, being sold to the continent? I don't know, but it's higher than in the United States. So we could just start with the United States as the prices 2 and 33, something like that, maybe. See the exchange rate? Last time I used this sheet was down around 6 crowns per dollar, and now it's more like 8.5. So this is to get both crowns and dollars for those who think in the different. This is an arbitrary initial gas in place. I've written, 10. If we write 1E12, that's a trillion standard cubic feet. That's for a North Sea field. Of course, in the United States, you don't find this size of gas reservoir, okay? But in the North Sea, if the gas field doesn't contain at least 10 to the 12th standard cubic feet of initial gas in place, it won't be developed, probably, okay? That's kind of the marginal size of an offshore North Sea gas reservoir. So that's, but it would be kind of a monster reservoir in the United States. that equivalent is given here in standard. This doesn't, let's see here, that doesn't look right. That should be divided by. Okay. I think, isn't that right? There's 35 standard cubic feet in a standard cubic meter. Anybody know the conversions? No? Okay. Let's go check it. Does anybody know why why this thing over on the right doesn't show up anymore? So I can scroll down.
But what's that hand next to the camera and the toolbar? Like next to tools, there's the clicked box. Yeah, this one. What is that?
There should be something over on the right. I don't know why there's not. The other thing is that I can't get the search to work. Control F. Select, search, find. It's not good. All right. I tell you. Here we go. Units. Mass volume. Doesn't have volume. My goodness. There we go. Gods are working gifts. Okay, so there's cubic feet, cubic meter, 35.31 cubic feet in a cubic meter. I'm pretty sure that's right. Yeah? Anybody disagree? Okay, so which means that the Excel sheet was not right. This wasn't really being used, but okay. So, and then it gives a kind of a expected gas recovery, 70%, which would be, you know, a decent gas recovery for gas condensate depleting down. And then it ends up that, for reasons you'll understand by the end of today, hopefully, we don't recover as much condensate as we do gas, okay? That's because when we go below the dew point, you get liquid dropping out of the gas, it sticks and hangs to the rock, and it doesn't come to the surface. So we're losing these heavy components, okay? And so the recovery of condensate is going to be less than the recovery of gas. And you don't need to know what this means here, but you can kind of see that in this table down here, what we're saying here, this is kind of the initial in situ oil-gas ratio. Okay, it's the reservoir fluid, and you take it to the surface, and if it makes 100 barrels per million standard cubic feet of gas, this is not particularly good. Standard cubic feet should be. That's the unit for field, and this is standard cubic meters per million standard cubic meter. So this is something around what I would call a normal gas condensate. I think Sleipner, which is the biggest gas condensate field in Norway, pretty sure, is around 100-ish barrels per million standard cubic feet, which is equivalent to 560 standard cubic meters of condensate per million standard cubic meter of gas. So if we're saying that if we recover 70% of all the gas that we have initially in place, we might only produce by depletion probably less than 55% of the condensate. This is kind of an empirical number, this 0.15%, but basically what this allows you to calculate is you've got the recovery percentage, you've got the initial in place somewhere here, that's the initial gas in place, and the initial condensate in place must be somewhere here. Let's see here. Well, let's just put it in there as a column, I guess. Well, okay. We're going to talk about oil-gas ratio, or as it's called in this spreadsheet, condensate-gas ratio. This is going to be the surface oil volume from a process to the surface gas volume. Okay, so we've got this reservoir that we've defined. We bring all of the material to the surface. We put it through some surface process. And we get this, what we call condensate, if this is a reservoir gas, reservoir with a dew point, and we get our surface gas. And the oil-gas ratio is just the ratio of the oil to the gas volume. The symbol for the SPE is little r for the oil-gas ratio. You have RP, which is the producing oil-gas ratio, and you have RS, which is the solution oil-gas ratio. And at initial conditions, we have the initial in situ solution oil-gas ratio. So in this spreadsheet, the initial gas in place, G, which is the symbol, is just going to be the surface gas produced. If you just took magically the entire reservoir to the surface, okay, through this process, the entire reservoir. So the surface gas produced, if you took the entire reservoir gas volume to the surface. Obviously, that's a fictitious number, but that's what we call the initial gas in place. This is a reservoir gas because at reservoir temperature it has a dew point. The initial oil in place, because when we do this magical processing of the reservoir gas to the surface, we also get something that's very important here, which is the initial condensate in place, or the initial oil in place. Again, this is for a gas condensate reservoir. So that's equal to the initial gas in place times, because that's basically this gas number here, times the value of R initially, initial solution oil gas ratio. So that's the surface oil or condensate. If again you took the entire reservoir gas volume to the surface. There is no oil phase in the reservoir, okay? But you still have initial oil in place at the surface. It's very important to understand that, okay? So if you say you have a gas reservoir and all you say, you start talking, and the president asks you, you're having lunch with the president or whoever, okay, and they say, well, what's the initial oil in place of this? And you say, well, it's a gas reservoir, there is no oil. That's not going to be the right answer, okay? There's going to be, probably, if it's a gas condensate reservoir, there's going to be initial oil in place. Now, in this spreadsheet that I'm showing you, it's basically specifying this initial gas in place. I changed it to 10 to the 12th standard cubic feet. I just, you just specify the number. Okay, that's this number up here. And I told you why I picked 10 to the 12th, because that's kind of like the small size for North Sea. Okay. If you pick Schleipner, I think it was around 7, 10 to the 12th. I don't know for sure. I can't, it's probably changed a little bit over time. But you basically can put whatever number you like here, and then this is just if you think in terms of crowns or standard cubic meters. I think this is now correct. Okay, now what's given here are different values if you say my reservoir contains a particular mixture, okay? And that mixture is described by the initial in situ CGR. So in a sense, these are different numbers that we specify here. We're not calculating, we're just kind of specifying them. I think this is calculated by units. This is, I'll put here as if it was red. This is calculated, converting it to a different unit. Now, what's not shown here, what is shown here is the initial gas in place. I can give it the term G, since that's, okay. What's not given here is the initial oil in place, okay? And there should be a column here with initial oil in place. So I'm going to mess things up a little bit. I'm going to add that column. I'm going to move all these things back. That. And here I'm going to put initial condensate in place. Well, I'm going to write oil just because there's You'll find it both ways, but initial oil in place. Okay, OGR. It's the same thing. And then I'll put it in stock tank barrels. Maybe I'll actually put it, yeah, stock tank barrels. I suppose I should have another column for your that. And this is just equal to the initial gas in place times the CGR or the OGR initial, or the little r SI. Okay. I'm going to save this here to our class exercises. Okay. Okay. So now I've got initial oil in place is just the initial gas in place. So that's going to change depending on what I say is my reservoir fluid. Okay, my reservoir fluid is, you know, this is Schleipner. This is the North Field. This is like in the range here, the largest in the world gas condensate reservoir is called the North Field. It's in Qatar. And there's about, as part of the same, it's in the Kuf Formation. It contains about, they say, 900 10 to the 12th. 900 10 to the 12th standard cubic feet. Okay? But its CGR is somewhere between 40 and 60 barrels per million. Okay? Now the Iranians, because Mother Nature didn't know about these boundaries when all this stuff was put in place, the same geological reservoir extends over into Iran, and it's called South Pars. And it, they say, has about 300 TCF, okay, with a similar CGR, though I don't really know because I'm American and I can't work in Iran, so I can't tell you, but it's the same reservoir, so it's about the same CGR. Smørbukk, that's our local gas condensate field here in Norway. There's 4 different formations. There's Tilje and I don't know. Anybody know the formations in Smørbukk? I should know them. Okay. This is a little bit embarrassing. There's 4 formations. Each one has a little different CGR, oil gas ratio. But they're in the range here. Okay? All the way from 300 barrels per million, the richest is very rich condensate, down to lower values. And it ranges as a function of depth in the different formations. So whatever reservoir you have, you can kind of go in and pick your number here. And then you can put your number up here. So we'll go back to the North Sea reservoir, 7 10 to the 12th. I think that's like Schleipner-like. We have to move these things back again, sorry. Okay. And so we've got our gas in place. Now to get the oil in place, we have to multiply by the OGR. Okay. And so that's oil gas ratio in stock tank barrels per million standard cubic feet times this one here, right? But that's not in million standard cubic feet. It's in standard cubic feet. Okay. So I have to fix the address on that and then divide by 10 to the 6th to get the units right. And then I want to put this in scientific. So 70 million barrels. 70 million barrels. But Schleipner, that's if you had a very low oil-gas ratio. We'll just copy this down here. For Schleipner, which is around here, I think, that's 700 million barrels, which is almost as a billion barrels, which is a lot of oil. Okay? Okay, we've got to calculate our standard cubic meters. I think there's 6.28 barrels per cubic meter. Is that right? Anybody know their conversions? All right. Let's go look at the barrels cubic meter. 6.29. Okay. 6.29. All right. Okay. You guys see this okay? So we've got basically standard cubic meters. That's our initial oil in place. And then this gas recovery factor, that's taken from some number up here. And for gas reservoirs, which we'll start talking about week after next, recoveries of gas reservoirs should typically be between 60 and 98%. Okay? 60 and 98% for gas. So we are using a value 70. And there's some kind of a loss. There's less recovery of condensate than there is of gas for reasons we'll talk about today. Okay? Because of the condensate that drops out of the gas in the reservoir and is not produced to the surface. So we have a lower recovery for the condensate. And you see it gets worse and worse. The richer the fluid, the more barrels you have in place, the less recovery you get. Okay? Okay. Mother Nature puts more in solution in the gas, but when you go below the dew point, a lot more drops out. So you get less recovery. Okay, so these are kind of like empirical. So to get the value, and this is not discounted or anything, so you should be able to take the value, would be the initial in place times the recovery factor times what? The price? Okay. So let's try to recalculate this. So we've got the initial in place in gas. That's this number up here. Times the recovery factor, which is here. Times the price, which is up here. We have to lock that. We also have to lock that. But the gas price is in dollars per MCF, right? But the gas volume is in SCF. So we have to divide by 1,000 to get the units right. And the unit here is million dollars. Okay? Now I've got dollars. If I want to show this in dollars, it's short of $1 billion. Is that right? But I want it in $1 million, so I have to divide again by 10 to the 6th. Okay. This still is not giving me, I think, the right number, but because here I've got 9,800, and here I've got something.
Yeah, I think the recovery factor has to be in fraction.
What's that?
The recovery factor.
Ah, there we go. This is in percentage.
Yeah.
So you have to divide by another 100. Thank you. So Curtis made 3 mistakes, okay? That means you guys can make at least 3 mistakes or more, okay? You have to be careful with units, and this is not the way to do it. The way to do it is to take your piece of paper and you actually calculate what's the value of gas. That's the initial gas in place, okay, in standard cubic feet, times the conversion, times the price, which is a recovery factor. If that's in percentage, then you have to divide it by 100 to get fraction, right? This we need in MCF because the price is in MCF, right? So we need 1 MCF is 1,000 standard cubic feet, right? This gives us gas in place in MCF. We got our price of gas, which is in dollars per MCF. So now we can cancel that with that. The fraction's okay, and we've got US dollars. That's what we want. But we don't want this. What we want this is in million of US dollars. Right? So this is all in dollars. Right? Then we have to multiply by, there's 10 to the 6th US dollars in a, is this what the finance people use for $1 million? Little m for million or not? Probably best not take a chance on it. All right, million of dollars as a unit. Okay. So you can see that you need to divide by 1,000, you need to divide by 100, you need to divide by 10 to the 6th. And instead of me doing it in my head wrong 2 or 3 times, dividing by 1,000, by 1,000,000, and by 100, you actually see it if you set it up correctly. Okay? So this whole thing here gives us what we wanted, which is in 10 to the 6th US dollar units. Right. Trump units. He doesn't think in dollars or thousands of dollars. I guess he thinks in millions of dollars.
This is
Okay?
billions.
Huh?
Billions, not millions.
If he thinks. I guess. Okay. So this is so this is the calculation that we, at least that looks consistent. And then on the condensate, we can we have to calculate the condensate value. So let's do that. That's the initial oil in place here times the recovery factor here, divided by 100 to get it in fraction, times the oil price up here, which is per dollars per barrel, and we are on barrels. And is that it? No, we want $1 million. We want Trump dollars. 10 to the 6. You think I'm supporting him, but I just like it looks like it's going to happen. Okay? And that was the same as we had? Or not? Well, we're not sure, but if we do this, yeah, we get the same number here. Okay? Okay, so I think we can just drag these down to copy. Okay. Now, for some strange reason, the percentage of value coming from gas would change. It shouldn't, I don't think. So I'm not sure what these... So these calculations should be G14, that's the gas value, divided by the sum of the values times 100. Yeah, that looks right. And that should be 100 minus that. So that's right. Looks right. So when we're down about here, in this range here, of CGRs from 60 to 80 barrels per million, we're making the same value from the oil and from the gas, according to these calculations. Of course, if you change the gas price to be higher, reflect a higher local gas price, I don't know what it is in oil, but let's say it's still $5 and maybe instead of what used to be 10, then this changes. So in that case, we'll always make more value from gas than from oil, if these calculations are right. I have to. Okay. So 2 years ago, this was like 3 in the United States and 110 in the United States. This was so then you can see that you get this transition at a much lower oil-gas ratio when you're getting more value from the oil than from the gas. All right, so I'll post this just as you can look at it yourself. There's probably some mistakes in it, but you can help find those and let me know. All right. The reason for going through this is to emphasize why this is key data. And this variation here is going to affect, in the calculations we just made, in the recovery factor of the surface oil. Okay? This is going to be less than the recovery factor of the surface gas, which will always be high. But how much less it is will depend precisely on how these components change the composition of the oil and the gas. Just think of it as like the humidity of air. The content of water in air is a strong function of temperature, right? Okay? Higher the temperature, the more air can take water in solution. Okay? But in our case, it's pressure that's changing. So basically, as the pressure drops, the gas is able to keep in solution less oil. Okay? So as the pressure drops below the dew point, oil comes out of solution. The oil has no mobility. It sticks to the rock. You don't get that oil. Okay? And that loss of recovery of the condensate is, in this spreadsheet, given through this kind of empirical Curtis adjustment. It's not correct, but it's just like it's an adjustment. So, okay. So we'll stop there.